Hi everybody. Today I'm going to talk to you guys about the energy that we find in an oscillating spring system. So we're talking about a spring pendulum, and we've probably done a demonstration or two about this in the past few days in class. But I want you to see what the formula looks like for it so that you can kind of get a sense for what we're talking about here and why we do it right after the energy unit. I think you'll recall that we have this force right here. And this is the spring force. This is the force that the spring applies to be able to restore itself to its original position. So if it originally looked like this, and you compressed it so it looks more like this, it is trying to push itself outward with a spring force. And that spring force right there is sort of dependent on a couple of things. Number one, it's dependent on the stiffness of the spring, which is a number value that we can give to that stiffness, which is represented by that K constant right there. And then how much you compress it. I think you'd agree, before you start to compress the spring, you're applying zero force to it. But as you compress it more and more and more, the force increases. And so as a result, if you think about it, if you wanted to do a force versus time graph like this for what it would take to compress the spring, look at what that would look like. It would look something like this. So originally you would go ahead and not apply any force. But then over time, as you compressed it more and more and more, you would end up with a force more like that. And so you can see this is not a constant. And so you may remember in class that we oftentimes deal with constant forces because it makes our math a little bit easier. And it's kind of simpler to talk about. This is not a case where we can do that, though. And so as a result, if we were going to talk about how much work is being done, we could take that same graph, and instead of doing force versus time, we could go ahead and do force versus distance. And you might remember that the work is actually equal to the average force being done multiplied by the distance over which it's being done. And so the area under this curve right here would tell us what that is. Now the area under a triangular curve like that would be 1/2 base times height. So because that's the area of a triangle, right? So area would equal 1/2 base times height. Now, if we look at it here, what's the base? Well, the base is actually that, right? That x. So I'm going to go ahead and put that in there here so you can see it. So we've got 1/2 times the x, the maximum x value, times the height. Now the height is actually this maximum force value. So the maximum force value would be the force on the spring at its highest point. Now the force on the spring at its highest point is actually this formula right here. And so what we end up with is 1/2 x, and I'm going to sub in this kx here for the spring force to try to simplify it as much as I can. So 1/2 x times kx, or if we look at it the right way, simplified, 1/2 kx squared. And so that is the area under the curve. And you might remember that an f versus x curve, if we're trying to find work, we can find the area under the curve, and that tells us what the work is. So this is actually the work that you have to do to be able to change the shape of a spring. 1/2 times k times x squared. Well, I think you'd agree that once you've done that work, it doesn't just go away, it becomes potential energy. And so this compressed spring has potential energy, and the stretched spring has potential energy as well. It's just in a different direction. And that's okay. We're not worried about direction with energy. So how much potential energy does it have? Well, it's all the work that you did becomes potential energy. And so you can see here we have the spring potential energy formula right there. The potential energy for a spring is 1/2 kx squared. And this x, again, is the maximum. Now we're not going to do a bunch with this, but I wanted you to be able to see it, because then what happens is if you release this, that the spring oscillates. And I think you guys saw that a little bit in class as I had a spring that oscillated against the force of gravity. Okay, so here we've got our spring. And at a later time, it was up here, and then it came back later on, it was back down here again, and then later on, it was here again, and so on. And so over time, you saw this kind of sine wave curve as it oscillated back and forth. So it has potential energy, and then kinetic energy, and then potential energy, and then kinetic energy, and then potential, kinetic, and potential. And so it oscillates back and forth as it exchanges that energy. Over time, though, I think you'll recall that the total energy stays the same, but the amount of the mechanical energy, which is the kinetic plus the potential, decreases. So that goes down, and the thermal energy goes up because there's this thing called damping, and we're going to talk about that in the next video. So hopefully that makes sense. So as it oscillates back and forth, like so, it's just exchanging energy. And what we're going to find is that oscillations like this, simple harmonic oscillations, are ways in which energy is transformed. And then, sorry, there we go. And then the energy that you have in the system, later on we'll find out when we talk about waves, the energy can be transmitted throughout a medium if the oscillators are connected in some way. That's it from here, as you saw with the lights going out there. If you have any questions, please let me know. Thanks for watching.